Hello and welcome to the first of our attempts at flip casting. Today we're going to talk about lesson 4.4, which is all about optimization. This is a review of things that we have already discussed, but these are very difficult problems and frequently part of the AP test, so we want to make sure that we have a good understanding here. Basically, optimization involves finding extreme values in word problems. And of course, to do that, we can use calculus and find the derivative of a function and simply set that equal to 0. So there's a general set of steps that we like to follow as we go through and do these problems. First of all, if we list out our problem-solving steps, there is generally a collection of steps that we go through in order to do these kinds of problems. Obviously, you have to read and understand the problem. Once you have that part done, the first step is to write an equation to be maximized or minimized. Okay. Secondly, we generally will have a constraint. There will be some restriction on the values that our variables can take. So we will also be writing a constraint equation, and we will do several examples in this lecture and get some sense of what we're looking at here. So write a constraint for the variables in the problem. And thirdly, we will find extreme values by taking a derivative. So when we go through and follow these steps, we find that we can solve the problem and get the answer that we need. So let's take a look at an example. Suppose we have a rectangle, and let's suppose that the base of this rectangle is on the x-axis, and its upper two vertices are on a parabola. So we'll do y equals 12 minus x squared. And again, this is an extreme value, so what is the largest area possible? We'll go ahead and find the maximum. Okay, and this may be a problem that you've already done in your textbook. So we can go through and check this. The first thing we're going to notice is that we do have a constraint here, and we can draw out a picture. The parabola y equals 12 minus x squared is going to look something like this. Up here will be 12. And so we have some rectangle with its base on the x-axis. And the other two vertices are defined by the fact that they have to be sitting on that parabola. So these 2 points here and here have to be part of the parabola, and that ends up being our constraint. That's the restriction we have on the points that we can choose. So let's go ahead and notice that there's some symmetry in this problem, right? We have the y-axis here, and our problem is symmetric with respect to that. So I'm going to go ahead and define x as simply the half width of our rectangle, and we'll go ahead and call y the height of our rectangle. Now, the first problem we want to do is the first step we want to do here is we want to write a function that we want to maximize, and we're told in the problem that we want to find the maximum value for the area. What's the largest area possible? Well, clearly the largest area here is simply going to be the base, which is 2 times the x value that I have here, times y, right? The general formula for the area of a rectangle is length times width. So we have this relationship for the area. Now you'll notice that this has 2 variables. We could go through and find the maximum of this function by using implicit differentiation, but we need to have some relationship for y. With 2 variables here, we can't solve the problem for a particular value. So we have to have a constraint. Well, it turns out that the constraint shows up with these 2 points here. Right? We are restricted. As soon as I have chosen my x value, then I'm forced to have a particular y value. So there's a connection there. And that connection is simply the equation that we have right here. This y equals 12 minus x squared. This is our constraint. This is the restriction on what the values of our function can be. So what we can do is we can combine these 2 equations to come up with a formula for the area that's expressed in only one variable. So I'm going to go ahead and write then that the area is equal to 2 times x. Now instead of y, we'll simply write 12 minus x squared. So here's a formula now for our area. We can go ahead and find the derivative of this area function. So we're going to go ahead and take the derivative of the area function. You could go through and distribute things here. I'm going to go ahead and just use the product rule. So the derivative of 2x is 2 times 12 minus x squared plus 2x times the derivative of 12 minus x squared, which will simply be a minus 2x. And again, what we're looking for here is we're looking for a situation where the rate of change of the area is 0. We're looking for a maximum value for the area. So we'll set this derivative equal to 0. That gives us 24 minus 2x squared minus 4x squared, or 0 is equal to 24 minus 6x squared. If we move the 6x squared over, that gives us 6x squared equals 24. X squared is equal to 4 then, and that tells us that x has to equal plus or minus 2. And of course we can choose either one of those. They give us the same rectangle. If you recall in the original statement of the problem, we said that x was the value here. And if that was negative, that would just mean that we were talking about this piece over here. So we have found a first derivative that's equal to 0. So the dimensions of our rectangle, this is another important point in these problems. Oftentimes we get to the spot where we have got the derivative and we say, yay, we have the derivative and we're done. We do need to make sure that we give the solutions to the answers. What rectangle has the largest area? X is 2, so that means that the width of our rectangle will be 4 units, and then the height of our rectangle will be 12 minus 2 squared, or 12 minus 4. The height will be 8. So a 4 by 8 rectangle will be the largest rectangle that will fit in the area underneath that parabola. And as you go through and look at the problem, again, you can see if you go back and rewatch this, you'll notice that we did follow those steps. There was a step 1. We wrote the equation that we were trying to maximize and minimize. The second step was to write an equation for constraint, combine those equations together, and then come up with the equation that we ended up taking the derivative of and finding the maximum by setting that derivative equal to 0. Okay, let's take a look at a slightly more difficult problem now. That one wasn't too bad. We'll see what we can come up with here. We'll do another one out of the textbook. This one is actually problem 15 on page 227. So page 227, problem 15. The question here is 2 sides of a triangle have fixed lengths A and B. And the angle between them is theta. Okay. And the question here is, what value of theta will maximize the triangle's area? And we're also given a hint here. One way to express the area of a triangle is area is 1/2 A times B times the sine of theta. So we will go through here and work to solve this problem. And again, we'll start by drawing a picture so we can see the problem that we're looking at. We have two sides of a triangle. We have side A, we have side B, and we're not told which is longer, which is bigger, anything like that. And we have some connecting angle here, theta. And the question we're asked is, what value of theta will maximize the area here? So we want to choose an angle that will make the area as large as possible. And sometimes it's good to just sort of explore the problem and see what changing that angle can do. Because we can make that angle very large, and you might think, wow, if I make that angle super large, it's going to give me a very big area. But only up until a point, right? If we think about extreme values for that angle, we could have side A here and side B here, and you'll see that we don't have a very large triangle. Likewise, if we choose a very small angle, you can see that again we don't have a very large angle that will give us a very small area as well. So there's some connection there between the area and the angle, and we're going to use calculus to figure that out. Now, one way in which this one is a little bit easier is that there is no equation for the constraint. There's only one unknown, that is theta. We can simply use the relationship that the area is 1/2 A times B times the sine of theta to come up with the relationship here. The thing that makes this problem a little bit more complicated is A and B are constants, but we don't have a value for them. So you may get tripped up trying to take derivatives where we have some constants here. But let's go ahead and take this derivative. So the derivative of the area with respect to changes in theta now, theta is our variable of integration or differentiation here, is going to be 1/2 AB. This is all constant out here, so this simply comes out in front. The only place where the theta shows up is in the sine function. So we take the derivative of sine, and that gives us cosine of theta. Now, in order for this to be a maximum, we can set this equal to 0. So we can say 0 equals 1/2 AB cosine theta. The only variable here is theta. And you'll notice that it doesn't matter what the size of A and B are. The area of the triangle will be maximized when we have 0 equal to cosine of theta. And that, of course, occurs, if you look back at your unit circle, that occurs with an angle of 90 degrees. So a right triangle, for given sides, a right triangle has a maximum area. I think that wraps it up for this discussion. I will post several more examples in another video. If you are interested in watching that, please feel free to do that. And again, that will be a link to that will be provided to you as soon as that is ready. So thank you very much, and good homework.